So let's finish up our notes here. Suppose the amount of oil pumped from one of the canyon wells in Whittier, California, decreases at a continuous rate of 10%. Right off the bat, when you see this, this is your hint. So something changes by a percentage, or it says, what was the phrasing they used last time? Can be shown by a differential, or no, that's not what I'm trying to say. Rate proportional, there it is. So using the words like proportional or things that are changing by a percentage or direct related, directly proportional. These are all a clue that dy over dt equals k times y, which also means y equals constant times e to the kt. So this thing we're going to use over and over and over again. And that's you want to think of this when you see that in the story. That's the hint that you're going to go that route. After how many years will the well's output fall to 1/5 of its present level? So I first have to figure out a couple things. I got to find K, and I'm going to use that K value to evaluate what happens when it's 1/5 of its present level. So how much is the oil? How much is in there right now? I don't know. It doesn't say. What's nice about that is you can pick whatever you want to be the beginning amount as long as it fits with the story. Now, usually I pick my beginning amount to be something like 1 because 1 is usually the easiest thing to calculate. But read this story a little bit more. Our story decreases by 10% each year. So if I use 1, I can use 1, but then I'm going to have 10% off of 1 is 0.9. And then from there, so I don't want to deal in decimal. So I'm going to choose my initial amount. Let's define our variables first. So we've got units. Suppose the oil pumped decreases at a continuous rate per year. Wells out. So it doesn't say. So we've got our time, and then I'm going to just call it A again, the amount of oil. They don't really say if it's measured in gallons or kilogallons or whatever. I don't know. Megagallons? Is there such a thing? Whatever. All right. So at time 0, I'm going to choose there to be 100 of these things in there. So what do we know? After how many years will the well's output fall to 1/5? So we don't know that yet. So we can go ahead and try to figure out what, using this information, let's see if we can now use our equation up here. So at time 0, there's 100 whatevers of oil. I have a hard time not getting units on that. So 100 equals CE to the K times T. Oh, sorry, time would be 0. So K times 0. K times 0 is 0. E to the 0 is 1. Therefore, C equals 0. Yes, that should be true. That's something that we talked about in the last video, that your initial amount is whatever this C stands for. That's your initial amount. So we could have cut that part out if we wanted to. I just wanted to remind you. So we have Y equals, actually I called it A, didn't I? A equals our initial amount, E to the K T. We don't know that. So now we have to figure out what K is. And let's think about it in terms of 1 year down the road. I mean, we can pick however much time we want, but we know that our story decreases by 10% each year. So after 1 year, how many units of oil would we have? We'd now have, well, think about it. How many units of oil would we now have? Well, if I'm losing 10% each year, after my first year, I would be down to 90. Now I can take this and I can plug and chug into this equation. 90 equals 100. E to the K, we don't know, multiplied by the time. The time is 1 year. Divide both sides by 100. I get 9/10. I'm going to clean that up right off the bat. E to the K times 1 is K. Who's keeping K from being by himself is E to the, and what kills E to the is natural log. So natural log of 9/10 equals K. Now, if you want to try to do the cleanup that we talked about last time, I think I'm going to try to clean things up at the very end. So now let's see what our equation looks like. So A equals 100. E to the, we said K was, I'm going to put that in parentheses. so I don't get confused on who's getting natural logged. That's a 9. E to the natural log of 9/10 times t. After how many years will the well's output fall to 1/5 of its present level? So how much how many units of oil would we have if we're at 1/5 of what of 100? So that would be at 20. 100 divided by 5 ends up being 20. So now I can do a little calculating here. 100 e to the natural log of 9/10 t. Oh, I just noticed we could have done a trick there to kill that off right off the bat. I think we're going to have to do it anyway. Yeah, well, we'll do it later. So I'm going to divide by 100. That gives us our 1/5. That makes sense because if we started with 1 unit of oil, when it falls to 1/5, that would be on this other side. And I'm going to have, actually, I'm going to do this right now. Remember, if you have, this is the same as t times the natural log of 9/10. You buy that? Right? Natural log of 9/10 times t. I could put the t out in front if I wanted to. Remember your properties of logs. You can take these things and you can bump them up to the exponent. So this is the same as the natural log of 9/10 to the power of t. So this is where all those exponent and log properties that we've been working on over the past 3 years finally come to become pretty useful. So I'm going to rewrite this now as e to the natural log of the quantity 9/10 to the t, and you're going to see why that's so nice, because the e to the and the natural log cancel each other out, and we get 1/5 equals 9/10 to the t. So we're still trying to get t by itself. So the easiest way is we're going to now have to undo. I wonder if there was a way I could have done this without that. If it was a plus, I could have. I have to think a little bit more about that. But I'm going to natural log both sides. So the natural log of 1/5 equals the natural log of 9/10 t. The reason we like to do that is now I can take this t from the exponent and I can bump it back down in front. So I can now put that out there. So we're going to go up to here. So I have natural log of 1/5 equals t times the natural log of 9/10. Who's keeping t from being by himself? The 9/10. So I'm going to divide that across. So t equals the natural log of 1/5 over the natural log of 9/10. This is a free response. You'd be done. You'd box it in. Oh, no, you wouldn't. No, you wouldn't. Why not? Why not? You don't have any units. So these are years. So you could box it in at that point. I think it's pretty unlikely that you will have this as a free response. This is more likely a multiple choice. So let's practice how to clean this up. So it will look like you would see as a multiple choice answer. I'm going to encourage you to pause and see how much cleaning up you can do. And then we'll come back and talk about it. So I've got natural log of 1/5. That's 5 to the negative 1. And then you could take that negative and bump it out in front of the log. So this would be the negative natural log of 5 over. This is the natural log of two things getting divided. So that's natural log of 9 subtract natural log of 10. And like we talked about in the last example, I think, or one of the examples from the last video, usually they take a negative and they put it with something that's already got a minus to try to reduce the number of negatives. So they're going to take that negative and they're going to bump it to the bottom, which is going to make this term the positive term, and it's going to make this term the negative term. Years. Ooh, I almost drew my box without my units. Without my units, I might as well put them here too, just for good measure. Suppose a population of fruit flies grows in proportion to the number of fruit flies in the population. It's a dead giveaway. That's the word that we're looking for. When you see this, this makes you think of D. Okay, what's our changing? We're going to go with, we'll go with P for population, P for population over time is equal to some constant times the population, which then therefore we know that there's a relationship where the population is equal to some constant or initial condition times e to the kt. Now this one's pretty nasty. I tried to solve it a bunch of different ways. If you can see my work over here, I tried to solve this thing a bunch of different ways, and then I watched Corpy, and he had an elegant answer, which every teacher always has the elegant answer after they've seen somebody else do it first. So the elegant answer, I started off, let me show you where I got to, and then I started to lose where I was going from there. So I used the story to help me try to come up with some coordinate points, because I'm trying to find this initial condition. So we have the time, which is measured in, days. We've got units. The units are days and then number of flies. So I'm just going to call that population. So there's 100 flies after 2 days. So one of my points is 2, 100. 2 days turns into 100 flies. And then my other point is at 4 days, there are 300 flies. That's not how they're changing at that spot. That's how many there actually were. So those are points. So I'm going to take this equation and I'm going to join it with these 2 points. So my population at 100 is equal to some constant, e to the some other constant times 2. And then 300 equals some constant, e to some other constant, but this time times 4. Now what I tried to do here is I tried to solve these things to try to get k by itself. So I took this and manipulated it so that I tried to get k by itself, and then I tried to get that k by itself, and then I could sub them in. And my results did not work out very well. My results kind of got me nowhere. So when I watched Corpy's video, he said, well, when we're solving a system, this is a system of equations. Remember back in Algebra 2, we would solve systems of equations, or even pre-calc. We did it last year. We did in Algebra 1 as well. You probably did it in geometry. I've never taught geometry, but I assume it's in there. So a lot of things you can do to 2 equations. You can add them up, you can subtract them, you can divide them, or you can multiply them together. So I'm going to choose to divide these 2 equations. So I'm going to take I'm going to call this equation 1. I'm going to call this equation 2. Divide equation 2 by equation 1. So that's going to look like 300 divided by 100 is 3. C divided by C is going to cancel, and then I'm going to have now I'm going to multiply these, 4k. I'm going to multiply these e to the 2k. Well, we have a common base here, which means that we can rewrite this as, I'm going to draw an equivalent arrow, implies arrow. So e to the 4k, it would be e to the 4k minus 2k, which implies 3 equals e to the 2k. And now I can get to work. Now I've got myself down to one variable. I can get to work. So farthest away from k is e, so I can natural log both sides. Farthest away from k is the 2. So k is equal to, I'm going to go with 1/2 natural log of 3. So all that work, that allowed us to find out what k was. Now we can take that k value and start to use it in our actual equation. Remember, this was, this was our equation. We don't know what big C or what the constant is yet, so we still have to go do that. So I'm going to take this, I'm going to plug it into one of these to try to figure out, remember how you would do that? You'd solve for x, and then you'd take the x and sub it back in to find out what y was. So I'm going to now take this and sub it back in to find out what C was. I might as well use the easier one. So 100 equals C times e to the k, which for us was 1/2 natural log of 3, times by 2. I like the looks of that because those things are going to clean up. So 100 equals C e to the natural log of 3. I like that even more. So those are going to cancel. So now 100 equals 3 times C. Divide by, we get C equals 100 over 3. Okay, how many, well, that could be the end of the story, right? We could stop there. Because remember, if you have this relationship, that C stands for your initial condition. If you wanted to, you could write the whole equation up. The whole equation would look something like this. Population is equal to 100 over 3 times e to the 1/2 natural log of 3 times t. There's my equation, but then plug in times 0. That would become 0. That would become e to the 0 would become 1, so our population would be 10/3. So what's the actual answer? The question is, how many flies were in the original population? There were 100 over 3 flies in the original population. That makes no sense considering you can't have 1/3 of a fly. But let's ignore that. Let's ignore that. I think we might have to make an adjustment. But let's pretend like it didn't. Last example for this section. Ooh, this is another AP problem, AP 2012. This is the free response question number 5. The rate at which a baby bird gains weight is proportional. And when I see this, I stop and I write myself a little note here. This is reminding me of a couple things. dy of dt is equal to k times y, which therefore means y is equal to some constant times e to the kt. I want to memorize that. I'm still in the process. This is my first year teaching it this way, so I haven't memorized it yet, but the more I write it, the more I'll be likely to remember it. Now, it turns out they give me later on what the actual, so I don't even really need that, but that's okay. It's still a good habit. So the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. All right, that's interesting. At time 0, when the baby bird is first weighed, it weighs 20 grams. So I'm going to make another note of that. So that's at time 0. We have 20, and I'm going to circle grams because that means we have units. We have grams and then we have days. So here's my other units. If B of t is the weight of the bird in grams, the first weight, then this is the change. This is how the bird's weight changes. Let y equals B of t be the solution with the initial condition. Oh, so that's same thing. Those are the same thing. They wrote it down for us. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So we have to figure out how fast is the weight changing. This formula tells us specifically how the weight changes over time at a certain weight. So let's first find how fast the weight is changing when it weighs 40 grams. So we would do 1/5 times 100 minus 40 equals 1/5. Let's say, what does B stand for? B is the weight of the bird. So I'm going to say when B equals 40 grams. I wish I would have written that a little nicer, but I didn't think of it until just now. 1/5, 140, that's 60. 1/5 of 60 is 12. 12 grams. I'll pick a different color. when B equals 70 grams, we would have 1/5 times 100 minus 70, which is 1/5 times 30, which is 6 grams. So when is the little birdie gaining more weight? Obviously, when it's a little bit young, when it weighs less, which kind of makes sense. When you weigh less, you're growing usually, and so you're gaining weight faster at that time. Let's see if you can think of a nice way. We haven't done a write-up in a long time. See if you can think of a nice way to write this up using a good argument. Let's try something like this. I'm hoping for something like this. Since 12 is greater than 6, nothing too fancy, then the bird gains weight faster when it weighs 40 grams. Kind of like our IVT and MVT arguments back in the day. So find D2B dt2. What does that mean? Leave a little note to yourself. Do you remember what this means? This just means the second derivative. Second derivative. So we want to take the derivative of the derivative. Then we're going to use this to explain why the graph of B cannot resemble the following graph. So this is what they think they're asking. Is this B? Would this be a good graph of B of t? Question mark. And we're going to try to use the second derivative to make an argument for or against that. So if I want to take the second derivative, that means I want to take the derivative of the first derivative. So we were given the first derivative right here. So let's start there. So the derivative of the first derivative is going to be the second derivative. So d2b dt2 equals. So the derivative of, I'm going to distribute this, I think. No, I'm not. Yeah, I'm gonna. So let's go up here and distribute. So this would be 20 minus 1/5 b. Yeah. Distribute. Derivative of 20 is 0. Derivative of negative 1/5 b is negative 1/5 b times b prime, right? Because you've got to do this. It's like a chain rule problem. So when you derive according to time, the derivative of 20 according to time is 0. We don't care about that. But we have to treat this like a chain rule problem. So the derivative of negative 1/5 b is negative 1/5 b prime. Remember that when we did derivatives according to like y, and then we did them according to x. We did so derive this y according to x. So we would derive y squared as 2y y prime, or we derive 2y. Sorry. I think I said that wrong. We derive y squared. Y squared's derivative would become 2y y prime, or dy dt. That's because we're deriving y according to another variable. We're deriving b according to time. So that means we have to attach it b prime. So what is b prime? Well, b prime is this. Right? They already told us what b prime was. So that's the same as negative 1/5 times, and we looked up above, and b prime was 1/5 times 100 minus b. So we can clean that up. Negative 1/5 times 1/5 is negative 1/25. 100 minus b. Is that it? That's, yeah. So they wanted to find the second derivative. I don't know how you're supposed to say this. You call that d squared b dt squared, or if you call it, I don't know. I just call it the second derivative. Now we want to use this to see if this is a good representation of this. So I thought about it this way. Well, you try it on your own. See if you can pause and think. Do you think this is is this function's second derivative this? So I thought about it that this is y double prime, and it's what kind of a graph? Well, if there's only one variable and it's to the power of 1, this is a linear graph. And then if y double prime is linear, then y prime has to be quadratic, which then implies that y must be cubic. And this is clearly not a cubic graph. It looks like a cube root graph, kind of. I think it's really a logistic graph. Logistic. We don't use that one very often. Anyway, that's how I thought about it. Corpy's was much nicer, as usual. He said, all right, well, look at this. Look at this function for certain values of b. So if b is less than 100, then d2b over the second derivative. So if this is something smaller than 100, this would be positive times a negative, so this would be negative. Well, what did we learn about back in our derivative tests in Unit 3, I guess it was? If the second derivative is less than 0, therefore, if the second derivative is less than 0, then b, the function b, must be what? Concave down. Now, I don't know where 100 is here, but clearly from times 0 until some value here, something like this, wherever this is, these are all concave up for sure, and that really doesn't fit with this argument. So if b is less than 100, well, where's 100 going to be? These are all concave up values. So if b is less than 100, our function has to be concave down. No way that works. No way. And then we could go the other route. I mean, the second route would be if b is greater than 100, then the second derivative. So if this is bigger than 100, this would be negative times another negative would be a positive. Therefore, b would have to be concave up for that section. So everything after 100, so it doesn't fit, right? I mean, I could pick this to be 100. That would have to be 100, actually. Now that I think about it, this is the only possible value for 100, because if we set this equal to 0, we would find that b equals 100 is when our graph has a point of inflection. All right, so anyway, that was sort of a long argument. Use separation of variables to find b of t, so we now want to solve this, the particular solution of the differential equation with b of 0 equals 20. So I'm going to go back to this stage. I want to organize this so that I can get my b stuff and my t stuff on either side and then try to solve it. So let's start off by rewriting the whole function. Maybe a nice purple. We haven't done a purple in this section. So dB of dt is equal to 1/5 times the quantity 100, subtract b. So my first instinct was to cross multiply here, to bump, or sorry, my bad, was to distribute here. But then when I distributed, I realized that I'd have to multiply this times the distribution, so it'd even actually get a lot messier. So I'm going to do this a little bit differently here. I'm going to just bump this. I'm going to take this chunk that's connected by multiply. I'm going to move it to here by divide, and then I'm going to multiply by dt. So I would have 1 over 100 minus b dB equals 1/5 dt. So there's my separation of variables, B stuff on one side, T stuff on the other. Now I can integrate. Well, as I try to integrate this, I run into a problem right away. I don't know the integral of 1 over 100 minus b. And it's not one of those arc trig situations. So how would you integrate this? Pause, think about it, see if you can do it. We've already done it. We've even done it. We did it last unit. Well, hopefully your math voice said that we could use a UDU on this. So I'm going to do a UDU. So U is equal to 100 minus B, which means du is equal to negative dB. So then I can go back to the old derivative stuff that we did. Okay, so how close are we? We're off by a negative. I need a negative to make it a negative dB, so I got to correct for that. This is now 1 over u, so the integral of 1 over u is natural log absolute u. So natural log absolute, and we said u was 100 minus b. Maybe it would take you a little bit longer to show out a little bit more work there. Go over here in the margins, use up all that space. But by the end of the calculation, you should get back to this spot. Okay, now I want to integrate 1/5. 1/5 is just a constant. What's the integral of a constant? It would be that constant times the variable. And don't forget your plus c, because this is not yet particular. So there's my general solution. And now I need to figure out the particular solution with where t is 0 and b is 20. So I'm going to actually change colors here. Let's go with pink. So negative natural log of absolute 100, subtract b would be 20, equals 1/5. T would be 0, plus c. So negative natural log of 80, I can drop the absolute values because 80 is positive. And then I get c equals negative natural log of 80. Yeah? Nice. So let's now plug this all back into, this is my c value. Now let's plug it into find our general solution. So what would that look like? I'm going to go over here because I think I'm going to need some more room. Negative natural log absolute 100 minus b equals 1/5 t, subtract natural log of 80. And don't forget, you're not done until you get big B by itself. So the particular solution is always solved for the variable. So we're going to have to get big B by itself. I'm going to kill it off. I'm going to start off with that negative. That should be the easiest thing. I'm going to divide both sides by a negative. So natural log of 100 subtract B equals, and that's just going to switch these around, natural log of 80 minus 1/5 t. Try it from there. See how you can take it from there. Obviously, what are you going to have to do next to get rid of this natural log? Going to have to do an e to the. So I can go now 100 minus b equals e to the natural log of 80 minus 1/5 t. Am I allowed to get rid of the plus or minus? I think no, I don't think so. So we should leave that in there for now. Plus or minus. And then I'm going to break this up. Remember, you got e to something, subtract something else. How does that clean up? This goes back to our properties. See if you can remember. Do you remember? Do you remember? Don't worry. Little Genesis there. Or was that just Phil Collins? I don't know. So we get 100 minus b equals plus or minus. Okay, so when you got e to the something, subtract something else. That's like saying e to the 7th minus 5. That's the same as e to the 7th over e to the 5th. So I can now break this up into e to the natural log of 80 over e. I'm going to go to t over 5 here instead of 1/5 t. T over 5 is the same thing. Then we're going to have to bump the 100 over. I want to get rid of this plus or minus. Can I get rid of that plus or minus? Can I get rid of that plus or minus? Well, if I put in 0 right now, well, let's see. Hold on. Let's do one more cleanup. 100 minus b equals plus or minus e to the natural log is 80 over, you know what? I'm going to bump that e to the up to the top. So let's try this again. 100 minus b is equal to plus or minus e to the natural log is 80. And then this e I'm going to bump up from the bottom, so that means I got to have a negative exponent. Now if I put 0 in here, this would be 80, and then 100 would be negative. So I want the positive one. So I don't actually need this anymore. I can get rid of that finally. So I'm going to now do minus 100 from both sides. So I would get negative b equals 80 e to the negative t over 5. Subtract 100. And because I am not yet down to b, I would divide both sides by a negative, which would make the 100 become the positive, and then the 80 e to the negative t over 5. Before I box it in, I want to check this one more time. So before I box this in, let's check this one more time. So I'm going to put 0 in here, and I should get 20 out. So if I put 0 there, that would become 0. E to the 0 is 1. That would become 80. 100 minus 80, yes. So let's say that I left that as a negative. That would make this a positive, and no, it wouldn't work. So yeah, we could kill that off when we kill it off. So this is now after tons and tons of work, that is now the particular solution. Phew. All right, that's it. That's it for separable differential equations. So hopefully you've been attacking the homework as you go through. If not, it's time to get going. Let me know what I can do to help. Good luck.